presentation. Today I'm going to talk to you about the change bias in oxide-based nanoparticles, not specifically iron oxide only, but I will put some examples. And I will make kind of a review of results on different systems with different morphologies, mixing experimental and theoretical simulation. Here's the outline of the talk. As I told you, I will make a small introduction to change bias phenomenology in nanoparticle systems. And then I will comment on some atomistic modeling. And after this, a series of examples of different experimental results and how have we tried to model them. So to start with, probably you all know that change bias phenomena refers to a shift in the hysteresis loop when cooling the sample under a certain magnetic field, and it is characterized by the displacement along the field axis together with sometimes an increase in the coercive field itself. So in this simple cartoon, I show you how the process develops along the field axis for the example of having a ferromagnet on top of the antiferromagnet. But today, I will focus on nanoparticles, in which the interface in between the two phases is not as clear as in the case of thin films, so things will not be that easy to model. Okay, it's on the contrary. So as you see in this cartoon, exchange bias has been, this shift in the hysteresis loop, let's say, have been observed in many different kinds of nanoparticle systems and also thin films. All of them having in common two different magnetic phases which are coupled together at some interface. The geometries here are mostly spherical, but they have also been obtained in some others, right? So what are the main ingredients necessary to understand why these phenomena happen? We must have an antiferromagnet which does not reverse with the magnetic field. We must have some kind of coupling at the interface between the two magnetic phases. And it turns out that the loop displacements that we observe after field cooling are due to uncompensated moments of the antiferromagnet. So there's a plethora of models which mostly work on many kinds of approximations with this complicated phenomena, but all of them refer to the thin film geometry. So for the nanoparticle case, models are not that feasible, right, from a theoretical point of view. And the open questions in the field are how the nature of the interface interaction is, how can we quantify the loop shifts, which are the reversals mechanism, or the resonance mechanism, or why is the reason of loop asymmetries present in the sample. So the microscopic origin of exchange bias is well characterized in some systems, but it's still an open question. In any case, thin film or nanoparticle embedded in a matrix is due to the close contact between the ferromagnetic part and some other antiferromagnetic phase. And this means that whatever the origin is, proximity effects and the phenomena happening at the interface, and maybe probably also in the bulk, come into play, are important. And this means that the atomic details are important. So if we want to give an explanation of it, we will have to revert to atomistic models, right? Having into account all the parameters coming into play. So, as I told you before, these are the guys responsible for the first observation in cobalt oxide nanoparticles. And apart from Gaussian nanoparticles, usually formed by a ferromagnetic core and an antiferromagnetic shell, exchange bias have been observed in other morphologies also. So let's make a fast review of the phenomenology of Gaussian nanoparticles in general. Something happened now. sorry. Apart from the increase in the coercive field, sometimes we also observe that due to the exchange bias, we can obtain increased blocking temperatures. There's a field cooling dependence of the exchange bias field. The exchange bias field depends on the particle size. Not only appears as an origin, you can also have an inverted particle with the antiferromagnet and the ferromagnet on the opposite case. And exchange bias has been obtained using a spin glass even. And there's been a demonstration that the roughness of the interface plays a clear role in the loop shift. And structural characterization of the interface has been tried specifically using neutron scattering very recently. So seeing all this, we should have kind of a simple and general model upon which we can study how the exchange bias emerges and what its microscopic origin. The model is simple. We have a core with a ferromagnetic coupling and a shell of different thickness, of certain thickness, antiferromagnetic coupled with antiferromagnetic coupling, mimicking what you find experimentally. And the interface in the case of a nanoparticle is not very well defined. It's defined as the spins that have some neighbor on the other side. And the coupling in between the core spins and the antiferromagnetic spins is not known. They cannot be accessed experimentally, so we can play with this parameter and see what happens. And the simulation results show you that these Monte Carlo simulations all the time, that field cooling, you see that some net magnetization appears at the interface in between the ferromagnetic and the ferromagnetic bar. So after the field cooling process, the core orders ferromagnetically, the shell antiferromagnetically, and the interface pins have a net magnetization. The magnetization of the interface pins is not zero, which is crucial to understand what happens. Right? And we will see in the next slides what's happening. So here you have the difference between field cooling and zero field cooling, and here you have the detail of what happens at the interfacial spins. You see that the reversal process at the interfacial spins is different in both cases. In the field cooled case, there's a net magnetization that doesn't change when cycling the field, and this gives rise to the horizontal loop shift. And this can be clearly demonstrated or quantified, at least from the simulations, by checking that as a function. Oh, again, I'm sorry that I don't know what I. Please, could you go back to my presentation? Every time I press a button. Okay. So there's a clear indication of this origin. If you compute the magnetizations, you can quantitatively deduce the exchange bias field by computing the magnetization of these two hysteresis loop branches and compare the result with the loop shift itself, and you see as a function of the exchange interaction. And we can deduce from here that the exchange bias can be quantified, and that the exchange bias field is associated to the uncompensated magnetization of the spins at the interface that do not reverse with the field. So this is the understanding that we can gain from a very simple model of a whole-shell nanoparticle. And now let's move to the main body of my talk, main part, in which I will make a journey towards through different nanoparticle systems which display experimentally exchange bias and try to unveil what is the origin with the help of some theory. So the first example is a single-phase nanoparticle, right? Many times exchange bias is observed in single-phase nanoparticles, but this is not a genuine exchange bias effect. You see a loop shift because you haven't reached saturation, as some examples in the previous talk with the antiferromagnet. And okay, For a single nanoparticle, single phase nanoparticle, iron oxide, magnetite or magnetite, the magnetic properties depend on the size, right? Because there's some kind of a disorder depending on the surface anisotropy of the particle and the size of the nanoparticle. This surface anisotropy increases or decreases depending on the size, and as you can see, the effect of increasing or decreasing the surface anisotropy is change completely the ferromagnetic character of the particle towards a more elongated hysteresis loop, with which sometimes when this loop is not extended to very high fields, induces some shift, which is due to this effect only. So apart from this, the composition dependence of the particle, I mean, the specific oxidation state also influences on the particle's magnetization at the individual level. So, sorry again. My first trials, my first attempts to simulate magnemite nanoparticle, some tens of years back ago, were with a single phase nanoparticle, right? And here you have the results. The first results that I got by Monte Carlo simulation were this, okay, at this place loop, right? But then it happened that I repeat the numerical experiment with a higher field, and I obtained no shift in the loop, which was the first time for me to realize that I need to couple the oxide to ferromagnetic part, otherwise the result that I observed is just, as I told you before, part of a minor loop and not genuine exchange values, right? There's no coupling in between two phases in a single phase nanoparticle. So, core shell nanoparticles synthesized are not really like in the model that I showed you before. As you can see here, not here, but here are some lines that separate different crystalline orientations on the shell. These particles form usually from a ferromagnet and then oxidizing the ferromagnet. So it's very difficult to have a single crystalline phase on top of a ferromagnet. So this matters, right? This existence of different crystallographic directions are very important, together with the surface effects and finite size effects associated to the individual particles. And two questions arise here, several questions arise in this kind of systems. Can the dynamic and static response of the core and the shell of the nanoparticles be identified separately? Can we perform experiments that demonstrate that the dynamics, performing an hysteresis loop, for example, for a particle, the dynamics of the core and the shell are different, and these give rise to the hysteresis loops here? Yes, as you can see here in this graph, this peak here in the blocking temperature marks the onset of a super spin glass behavior below this temperature, from which, apart from this, you can study the thermoremanence of the particles, and you can deduce, from these measurements, you can deduce the temperature below which the shell and the core become frozen magnetically. Also, by studying how this blocking temperature behaves as a function of the field, we see two clear, distinct regimes. One at low fields, which is dominated by the core behavior, and one at high fields. This is Almeida-Faure's lines characteristic of spin glass phases, which is dominated by the surface effects. So, through this series of experimental evidences, we can see that also that the loop shifts of these particles that appear below a certain temperature are, the loop shifts increase below the freezing of the surface spins. So this highly frustrated shell of spins on top of this ferromagnet is responsible for the exchange bias increase below a certain temperature. What else? Can we decouple, just another question, can we decouple collective contributions to exchange bias from the interface and the surface spins in a core shell nanoparticle? I mean, can we distinguish in between surface effects, which sometimes gives you a loop shift, and interfacial effects? You can do this if you study particles with different sizes, the ore-core particles with different sizes, but having the same size of the shell. From these experiments, one can deduce what is the magnetization associated to the frozen spins contribution. And we can also study, which is plotted here in red, as a function of the particle size, is decreasing in this direction, not this size. And we can also plot the exchange bias field as a function of the particle size. And what we see here is that the exchange bias for a big particle is lower than for a small one, whereas the fraction of frozen spins behaves in the contrary. So we see a change in tendency here, which separates interfacial effects for bigger particles from surface-dominated effects in the exchange bias for smaller particles. And we can deduce this by performing the correct experiments. Now, we come to simulations of these more difficult structures. These nanoparticles that I was telling you before can be synthesized, these core shells can be synthesized with different sizes here of the shells, having the same core, but varying the thickness of the shell. These are experimental results, right? Again, these are cobalt oxide nanoparticles, but in this case, you can also see that they have some crystallites on the surface. And I will show you now that it turns out that this is crucial to understand the shape of the hysteresis loops. The blue ones are at very low temperature. You see a very anomalous behavior here in both three cases. They depart from the typical square ferromagnetic loop, and they depart from any other characteristic loop of an iron oxide single-phase nanoparticle. Please notice here that this other particle is kind of a yolk shell, right? It's like the ferromagnetic part of the core is in contact only, slightly in contact, like an egg, right, with the shell. And so we will study these ones also. And you see that qualitative change in the hysteresis loop and the magnetization reversal mechanism. And the nice thing about the atomistic simulations is that you can separate the contributions to the hysteresis loop coming from the shell itself and from the core. And you can see the trend here matches perfectly what is seen in the experiment. We increase the shell thickness, and we see how this affects the magnetization reversal, and in turn, when increasing the shell thickness, the shell dominates the behavior more and more, the more we group the shell. And what we can demonstrate here is that by considering only contact of a ferromagnet with a shell, antiferromagnetic shell, formed of crystallites, with only a very small contact at the interface, a difference from here, we observe sizable hysteresis loop, right? So it's not necessary to have a big interfacial contact in between the two phases. A little contact here, maybe it's enough, because at the end, what matters is the amount of non-compensated magnetization that you have at the interface, not how much interface you have. Right? So, moreover, the simulations allow us to compare what happens when we have a single crystalline shell and when we have these crystallites on the surface. You see that the behavior is completely different. This matches the experimental results, and this one doesn't. And also we can study again what happens at the interface spins only. Some fraction of the spins do not reverse when reversing the field, giving rise to the exchange bias. And you can see also that the experiments demonstrate that thicker shell thicknesses, thicker shells produce higher exchange bias than thinner ones, as also, which correlates pretty well with the Monte Carlo results. And notice also that these guys have the highest exchange bias as compared to any core shell particles. Okay. So this is peculiar morphology, if you want. Moving ahead, you can study experimentally if you can control the oxidation of a cobalt seed, for example, and keep on oxidizing without varying now the particle size, okay, the total particle size stays constant, and then we keep oxidizing the cobalt particle, increasing the shell thickness in a controlled way. You see here how the hysteresis loop changes, and you see here how the crystallite size of the cobalt oxide changes as a function of the annealing temperature, which is the way to control the thickness. And here you can see the lattice parameter, how it changes with the size of the shell. And you see that there's a dip here, and there's a maximum here, which is indicative that some kind of strain, when growing an oxide on top of a ferromagnet, happens at the interface. And this translates in the appearance of a maximum of the hysteresis loop shift for some intermediate composition, right, thickness, which corresponds to this lattice contraction and expansion, which means that in this case, what happens at the interface is that the stress generated there because of the presence of the thick shell is inducing some increased surface anisotropy, which again increases the exchange bias field. And simulations of this real-size nanoparticles, which are big for the simulation, this involves hundreds of thousands of spins, agree well with this non-monotonous behavior. You can even match which spins, the most lighter here, do not reverse at the interface exactly, right? And you can see that the guys on the inside reverse more than the guys in touch with the shell, which are the ones in black here, right? So again, the atomistic level matters in order to understand how all this phenomenology. Okay, now we change geometry, right? Now instead of core shells, when you see in the process of synthesis of a core shell, you can continue oxidizing the particle, and then what happens is through the so-called Kirkendall effect, you have a vacancy migration to the outside of the particle, and you end up at the end not with a core shell, but with an empty particle, right? Which is a shell itself, what we call a hollow nanoparticle, right? Cobalt or oxide nanoparticle. A very characteristic thing of these particles, these are magamite particles, right? And you notice here the very low magnetization, 2 imograms when you project, or 4 imograms when you project from high fields, right? Which means that, and why is this so? I mean, having a void particle doesn't mean that you lose all the magnetization of magamite, which is more than 80 imograms. Why is this happening? This is an indication that, as I told you before, the hollows are not monocrystalline. Due to this vacancy migration process, they have clear crystals and different orientation, and these are responsible for this high frustration and high fraction of surface spins that they have. And the competition between the magnetic domains trying to form in each crystallite, and the surface effects gives you rise to this peculiar magnetic behavior, right? So comparing the hollow particles to the full ones, the solid nanoparticles, the hollow ones have a huge anisotropy, right? And also there's as you can see here, a very strong shift of the loops when you fill cool them, and we will try to understand this in the next slide. For this, I mean, we run simulations of a core particle, which took into hollow particle took into account the presence of these crystallites, right, and also the exact structure of magamite or magnetite, right, at the atomistic level. You can see here how the particle orders at low temperature, and you can see here, for example, what the results of changing the shell thickness, increasing the shell thickness or decreasing the shell thickness in red here, changes the hysteresis loop behavior. And another thing that you can understand, again, is that performing the hysteresis loop and the field pooling conditions in the two different fields, and comparing with the zero field pool, what you observe is an apparent loop shift, like in this red one, that when field pooling in higher fields becomes non-shifted, right? So again, we have here an example of a particle which is hollow, which is only ferrimagnetic because it's magnetite magnetite, and displays a change bias. But in this case, the warning is that it is a minor loop effect. There's no coupling or freezing of anything in principle that gives you this loop shift. And other effects can be studied in hollow nanoparticles, and one can we answer these two questions, for example? Can one tune this minor loop behavior that I just commented before by varying the number of surface spins, for example, is one question. And the other is, can we decouple now the contribution to the hysteresis loop of the spins coming from the external surface and the ones inside the hole, inside the void? And it turns out that, okay, doing the appropriate measurements and analyzing correctly them, we can compare here, for example, if you want to answer the first question, we can compare the properties of small hollows and bigger hollows, and you see that for smaller hollows, you see change bias, but okay, these are clear minor loop effects. When the particles become bigger, you see that the exchange bias becomes an intrinsic effect, a genuine effect. And the nice thing is that by fitting these loops at high temperature to two contributions, one coming from super paramagnetic Langevin and the other one coming from a paramagnetic phase, which would correspond to the influence of the surface disrupted spins, right? You can fit and decouple both contributions. And what you see here is that for small nanoparticles, for these ones, which what dominates is the paramagnetic contribution. So what dominates is the uncompensated spins at the surface. And therefore, we don't have a genuine exchange bias. This is a result of the strong frustration at the surface of the particles, which dominates when the particles are small. In contrast, for bigger particles, the hysteresis loop is completely dominated by the supraparamagnetic fraction, which corresponds to the reversal of the inside of each of these crystallites. Right? Moreover, nice thing with Monte Carlo is that you can simulate these particles again, and here I'm plotting, for example, how the outer and inner surfaces evolve with the magnetic field, and you can see that the contrast, well, it's difficult to see on the screen, but analyzing the different, the reversal mechanism, you can understand that the inner and outer surfaces reverse in a different way. And you can see this very clearly here. This is the inner surface contribution to the hysteresis loop and the outer one. You see that the inner surface spins are more easily magnetized than the outer spins, right? And you can distinguish this by performing simulations. So experimentally, it would be almost too much to ask, right? Moreover, you can compare the hysteresis loop of a hollow and a solid particle and see how where the origin of the differences comes from, and also explain the draining effects in these nanoparticles as changing the behavior of the hollow geometry when you make a void in the inside. And last example, which I'm short of time, I just want to show you that exchange bias may appear in when a magnetic particle is coupled to a non-magnetic phase. Like here, we could study what happens when we nucleate on top of gold, for example, nanoparticles of different sizes. And by synthesis methods, you are able to generate a flower, right? First attaching one nanoparticle and then several petals of nanoparticles, which and then compare the hysteresis loop And you see that there's a huge hysteresis loop, which increases from this case to this case, from the case when the gold nanoparticle is detached, which means that controlling the surface of contact in between the gold and the number of interfaces of this case with respect to this one, we are able to control the change values. It turns out that in this case, there's a strong lattice mismatch in between the gold and the magnetite, and this is responsible for the increase in isotropy at the interface of contact, and therefore we believe that in this case that the stress present at the interfacial layers in contact with the gold gives us this strong surface disorder, which is responsible for the hysteresis loop shift, as can be also contrasted with simulations, right? And since I'm short of time, I think this is my last slide. Thanks to all the collaborators which has contributed to this work, to parts of the work that I presented, to the group I belong to, and I move just fast to the conclusions for you to read probably, and just mention one thing, if you allow me, that we need to go, all these simulations are performed for single nanoparticles, studying one nanoparticle. Of course, you have a bunch of nanoparticles mixed together, and we should be able to understand what happens to the collective dynamics of a whole bunch of particles with having into account the surface effects, right? Dipole interactions between the giant spins, let's say, but also finite size and surface effects. And this is very demanding computationally, but it is on the way. And with the promise to show you the results in the next conference, or maybe in the next conference meeting of this ICSM, I thank you for your attention, and if you have any questions, you are welcome. Okay. Since I've been presenting many different particle systems, and to be honest, I'm not responsible for the synthesis, I cannot answer with one sentence because every system has its own synthesis method. But in general, in order to control accurately the compositions and the growth of the particles is metallic decomposition, chemical synthesis. So you need to control every step of the synthesis, the temperature, and the way you raise the temperature in order to be sure that the particle will nucleate correctly and so on. And in the case of hollow nanoparticles, there's this, I showed it in one of the slides, I'm not going back to it, but you can control the chemical reaction as a function of time changing how the temperature increases, and then you can control how the iron ions and the oxygen ions flow from the inside to the outside, which is the Kirkendall effect, exactly. And then controlling this process chemically, you can control it somehow, I mean not exactly, because I showed you this different orientation of the crystallites, the thickness and the global size of the hollows in that case, and so on. And for the golden ones, I mean, you have a gold seed, and then by these chemical methods, you try to grow a seed of nanoparticle, and changing the conditions of the reaction, you can grow several of them or just only one. So all these and much more.
So I have a question on the iron nanoparticles. That
Yeah.
You say that the change bias field change with the thickness of the shell. Could you elaborate a bit more, because I don't really understand why the change bias field changes, because I could understand that the shape of the loop would change, but not the change bias.
Well, it may change because of several reasons. You know, there are two reasons. On the one side, changing the thickness, right, of the shell changes the reversal mode of the spins on the shell itself. Now that the shell is depending on the morphology of the particle, right? Because you have this crystallites, and it's essential. Otherwise, I mean, all the shell would be frozen, right? Because you're assuming that the antiparamagnet stays in the same direction. Change. Due to the presence of these crystallites, and then you have an interplay between both things. Moreover, the surface of contact may vary with the size of the nucleus of the paramagnet in a non-monotonous way. You know, no, I mean, not exactly the phase, because I mean the interface surface increases. That's clear. But the number of uncompensated spins that you have when you cut the particle with this size or this size may change even right.
So you mean that if you have, let's say, an extended field, and you want
Yeah,
to
and in an
have
extended field, you
you
know that if you have perfect matching,
yeah.
you know how many uncompensated spins. You can count them, depending on the light. If there's roughness, it's more complicated. But in the geometry,
Yeah.
I mean, you got that like this, and you have perfectly compensation. You got a little bit more, and you got some spins up and down, and they do not compensate. And moreover, when you increase the thickness, the reversal mechanism changes because you have more force spins inside the surface, right, itself. And this could nucleate some structures there that affect also the. That's what I see in the simulation, right? That the reversal mechanism changes when changing the thickness.
Okay, I would like to ask you a question. So, this study is actually very useful for other kinds of physical system. Maybe you can make a connection with superconductivity because it's the kind of size effect, how it affect the structure, how affect the critical temperature of the superconductivity. So, have you ever tried this kind of study?
No, because well, I mean, we can discuss it later, but I don't see the connection of the magnetic properties themselves as I, in my point of view, I face them compared to the conductivity itself. No, I never thought about this.
Okay, thank you so much. Yeah, thank you. Thank you.